Hello, ladies and gentlemen. My name is Jerzy Baranowski, and welcome to the third part of our lecture on one-parameter models in STAN. This will be a shorter video in which we will consider the model of number of cancer cases throughout the entire United States of America. And we'll be using the dataset and example from Gellman's book, Bayesian Data Analysis, third edition. And for this, we'll consider again STAN model, and we will consider a special case when we will be fitting multiple models using the same prior for different counties. So, without further ado, let's move to this model.
This is an example of, again from Gellman's book, about kidney cancer. And kidney and actually the ureter cancer are very rare. And those cancers are, again, we have a data from the 80s, and it's a very simple, very curious situation that when considering the flights, counties in the United States, and observing the numbers of of deaths from those kidney and ureter cancers, there's a very specific situation. When you look at the highest and lowest percent deaths in the entire population, there's something wrong. Something wrong is that looking at when there's similar patterns of close neighboring counties, because like the county is a lower level than the state in the United States. At least that's that I assume. And the patterns are very similar, and those are caused by the fact that here we have the percentages. We don't have the number of cases. We have the how many cases per relative to number of population. And looking at that, if those counties here in the middle of the country are very small, and they are small around, they can be of population of 50 people, 100 people, 1,000 people, and certain cities are counties of population of 8 million people. So we have a lot of spread here, and this rate, while the rate of this is a rare disease, so when in large populations you would have rather good representation of this probability by having a very large number of people and modest number of cases. In case of small populations, if one case happens, then it's a drop, right? And if it's a small population, zero happens, it's normal. There's nothing happened, so we have a zero case. So this is there will be those lowest cases. So again, such spreading doesn't look like here. And that's why we want to create a model that will be able to get some kind of information from that as to how to estimate this. And we'll be doing a modeling with an informed prior. So we will have the certain prior distribution that assigns us initial probability of having cancer. And we'll be modeling each county individually. We'll be modeling this county individually by having the number of death cases in there, which might be zero, and we'll have considered the 10-year period, because we're 10 years later, right? And we have our exposure, which is our population, and we have our intensity, so how often the deaths from this cancer happen, and we have an informative prior distribution for our intensity, which gives us information where it is located. And how this distribution was assigned, you can find in Gellman's book. It's not like a right way to do it. It's not right way to do it when evaluating certain cases, but in practical analysis. But for our case, it was okay because it was done by moment matching. You can read it in the book, which I remind you, it's freely available, and the link was in the last lecture. So we will be moving to this case. So our cancer rate, I'll just move a bit faster. So we will not be doing it too boring for you, hopefully. And we have 3,700 counties. We are using the model I've showed you before with a gamma distribution, which, as you can see, there is a very low probability of death of this cancer happening. So this is the this probability is small, and this probability distribution give us some information. And we can, of course, repeat our idea to create some prior predicted distribution. So having our model, we provided the population, we sample from our prior distribution, we take theta, and using our model we sample how many deaths should happen for that population. And for example, for a population of 1,000 people, we can get such situation that we'll have between 0 and 3 deaths of that in the 10-year period, and we'll have the distribution is consistent, of course, with the with our prior. And it's like, as you can see, the mean rate of the theta is also very well located here, is around 4 times 10 to minus 5. We have our data set. As you can see, the data set is, okay, so you will have it available if you want to play with it later. And we have here observed death rate per 100,000 people, which we won't be using that much. However, we have the population and death count for every county in a state and state pair here. So we have a county and a state. The name of counties can repeat, so you need to be aware of that when analyzing this data. So those pairs have to be used together. And we are starting our work again with prior we've did our prior distribution for a single experimental town. So let's do it for our posterior estimation. So we have our model. We have the observed case at each observation of each county. We have a population of each county. We want to estimate our death parameters, and we are using a transformed parameter block because previously we just assigned this theta times time exposure, our exposure times intensity directly to Poisson distribution. And in our case here, we will save the parameters of lambda separately. So we'll create a transformed parameters that is a function of, in this case, data and parameters. And that can be useful in order to, for example, see how the rates behave here, or it can be useful in order to do more complicated models, which we, for example, discuss in the next lecture, how transformed parameters can be more useful, make model more legible, or multiple different things, or again those can be analyzed separately. So having that, our model uses transform parameter lambda. So as you can see, we assign prior for theta, which is used in the transformed parameters to compute lambda, and this lambda is used here. So it makes more and less legible at the same time. And of course, we are generating quantities, so we are sampling how many is possible from each lambda. We compile our model. And for example, we can do this test from here. As you can see, I've already extracted the values from the data frame directly as integer values from here. And for example, having one city, for example, county number of 575 from our data frame, we get the data. So number of deaths and the population. We sample, we check those diagnostics, everything works nice. We can sample it, everything works. And what we are doing here, in order to analyze all of those, well, there are certain issues. Because we could create a big 3,700 parameter model. And it doesn't look that well. Because there are some problems with numerics because of multiple rates, multiple size of populations, and we have larger populations of millions, and we have a small population of 50 people. The smallest one county has 50 people population, and in order to do so, we'll have to do a lot of tricks in order to have it working, and creating a single model that will estimate all the parameters at the same time will be counterproductive. And of course, it won't be a single parameter model. So it will be very easy to code, but it doesn't work that well, and I don't see a reason for tuning it at the moment to get better results. So in order to handle it better, I've just created a function that will estimate death rates and populations for each of the counties, and just providing it by appropriate county and population, it will return us a pandas series, which we will then be able to append to our original data frame of what's going on here. So this is this computation that's happening here, and so we are just sampling, getting parameters, compute median of theta, median of simulated depths, and create the 90% in this case highest posterior density interval. And this function allows us to again, remember, the quantiles here as not, there is nothing sacred in 0.95. As long as you know what you are doing, you're consistent with single analysis, you can use 90, you can say 89%, you can use whatever you want. Just so it makes sense, so don't use 20% confidence intervals because it doesn't make sense. And we have this situation here. We just create this data frame. It doesn't look too pretty, but it fulfills its purpose. And for example, for this county before we can predict the date rate, predict the death count, and with error bars for each value. So getting the lower and upper bounds of the confidence interval. So what we are doing here, this will be for you when you try to run this code here, because you won't be provided with this file. You will be the function will be called and applied to our data frame. So it will just take values from our data frame, and for each row it will perform the appropriate computation and append right columns here. So our finalized data frame, which will be here, is given here. I just noticed that it will always, because I haven't been added save to the counts and estimates data frame, but this is like this. I'll add it later. You will, in the version you will have, it will be corrected. So it has, the data frame is appended by right values of predicted errors, and for example, from our county from population of 1,000 that we've sampled from initially in prior predicted distribution is Washaba, San Diego. Not really sure. Maybe I should left the full state names. Either way, you should that's why when non-American does analysis of American data. Either way, what we are doing here is we have all the information. So let's now observe how it looks in comparison to our previous work. And in order to do so, we will be computing our we'll be seeing how our data corresponds to our model. And to visualize that, we will be using an error bar plot. So the plot that gives us the interval for each of the variables, and we'll compute them here just from our columns of the matrix, just so it will be corresponding to the error bar function of matplotlib. And what we are having here we have our as a function we have the observed death rate, which we computed individually for this one, so on the same scale, and we have a predicted death rate. And what's going on? What's happening here is that in case of we have something called the effect called shrinkage, that we in our case of our model, those values, for those predictions from generally, if our model would be predicting actual death rate that was observed in certain counties, then all those points should be on this line. This line is the the relationship between death rate and like if death rate was predicted death rate was the same as the observed death rate, so the count of deaths to the population, then we would have location of this line. But this is not necessarily good representation, because there are certain counties that we have 0 observed cases, but still the cancer is possible. So then the prior takes responsibility for everything. And in other cases, when we have a lot of data, then our samples are being more drawn to our data is giving us something different than the prior, drawn us through to the certain rate. So if we have observed information, then we have certain move here. And as you can see, everything is being drawn. For the higher rates are being drawn down, the lower rates are being drawn up to our prior, because our prior is an informative one, so it gives us where the expected deaths death count is located. And this prediction is not really like that special, especially that we have this prior that is not very strange. But let's compare it to how our predicted death counts look on the population scale. And again, the larger number of population, we will have a large number of death counts, as you can see, fixed here in a logarithmic scale. And you can see that our error bars and our predictions for each of the populations, depending on the estimated death rate. And those death rates, as you can see, are much varying on the population, except on although the counts, because for larger populations, of course, the counts will be larger. And let's look at what's this point. This point shows that for a very large population, we have this very low predicted death count. Why is that? This is Los Angeles, and for Los Angeles, we have no reported values of our no reported deaths of this cancer, which is evidently a missing data point. This is not the actual statistics. That just don't have the information about it. If we've just drawn all the data together in order to estimate our death count, there will be a problem, because that will make the situation more difficult. And as you can see, still our prediction is not 0, it's moved away, because the prior, despite the very large population, still drawn us to a bit away from it. So it compensates from the death rate compensating with the populations to get us somewhere here. And it gives a predicted death count of 19, so gives us, there still is possibility of death counts here, deaths here, despite that the data, which is wrong, says differently. And our model, on the other hand, very much better behaves as a prediction of actual deaths. So when we compare the prediction of death counts in the with the actual deaths actual death counts, well, this situation is much different. And in this case, this model behaves much better, because despite the fact that the death counts are different than the rates we observe, but the rates are very noisy statistics. They don't give us much information, because either they are they can be skewed by some things. They are in only a certain observation, or for small counties they might be very problematic. For large counties, missing data points might be very problematic. And in our case, as you can see here, the correspondence of predicted deaths is very strongly linear. So generally our model is very consistent with our error bars are wide, but they are capturing what is what's important here, and our predicted death count is very close to the observed death count. So our model is fit well, but there are some our models, because generally we have an assembly of models for each of those separate counties, and joining this data requires for more advanced approaches, for example, a hierarchical model, which might be doing later. So this is the here we have a zoom for of this space here. So for very small amounts of numbers of deaths, as you can see, because is also here. However, as you can see, the error bar is standing more higher. Why? Because generally the model is predicting that prior says that the more deaths should be happening than that was observed. So our prediction gives us the more value than higher value that was actually observed, especially for zero values, that something should be going here. So generally, what we had here, we took a model with an informative prior, and this informative prior allowed us to handle the discrepancies between large and small counties, because large counties have a lot of data or no data in case of Los Angeles, and their estimates are their estimates might be correct with response to actual model, but our prior keeping is everything in generally right points. And in case of smaller counties where we have very little data, probably no deaths, we still having this prior information, we know that this cancer is still a possibility, it can happen, and that's why. And in the hierarchical modeling approach, we will be estimating also the prior parameters for the cancer. So we'll be kind of estimating what is the probability of cancer in general in the group, and then using our data would have predictions for our certain areas. But this model that we might revisit on the later date. And finally, we are kind of exhausted all we can say about single parameter models. We haven't talked about Bernoulli distribution, which is a single binary trial. So it's like a binomial distribution, but only n equal to 1. So not that much that interesting in this case, but important in, for example, in case of classification on the stuff. So. But we will be doing it usually in connection with much more complicated models, so then Bernoulli distribution will make it return. And exponential distribution is good for modeling of waiting times. This is a continuous distribution with one parameter that determines its mean, and this parameter allows returns us real positive numbers. It's a slightly more tick-tailed than half-normal distribution, with a different shape because it's an exponential function. So the higher value, the lower probability. And I didn't have a nice case that will show us. Maybe we'll return to exponential distribution later. And of course, when you find literature single parameter models, you have the more complicated distributions, for example, normal, with some of the parameters fixed, and we'll just discuss all the parameters all together. I think that we've discussed everything that we can say about those simplest models, that even if they are simple, still the consideration from the start to the end might be exhausting and might take us a lot of work. And again, the lecture that I've planned for 15 to 30 minutes took us an hour and a bit. So thank you very much for listening, and hopefully it was interesting for you. So thank you, and see you next time.
Thank you very much for listening. I hope that this lecture wasn't boring to you. As I stated before, the first video, all the case study files on GitHub have been updated with commands done by a code, so you will be able to execute them without using Python, and all the code examples work and can be used, at least for this lecture. Other examples will be updated very soon. So if you want to try them, feel free to run them on your computer and see how everything works. Thank you very much, and have a nice day.